Hi, and welcome back to Integrated Science. This is Miss Sparks. This is a continuation of our previous notes on electricity and static electricity in particular. So do get out a sheet of paper and a pencil and take some notes today as we continue to talk about our circuits. So previously I introduced the idea that static electricity is just energy that is waiting as we have systems that clearly involved particles of our atoms, our protons, neutrons, and electrons. Our protons have a positive charge, our electrons have a negative charge. And as we put them through a system, we can create a circuit or electrical flow of energy. So think about just things that you use on a daily basis that you may have to charge. You are creating electrical current going through them, and it's charging up the energy. It's storing up protons and electron energy so that it can be used throughout the day, such as your phone, your Chromebook, your house even has it. So thinking about just turning on and off a light, you're just connecting and disconnecting the current, allowing energy to flow through the system. So once again, this has to do with our energy of positive and negative, which also then has to go back to the idea of our potential and our kinetic energy. And so we're going to kind of continue to talk about what this looks like. So once again, a circuit in general is just a system of conductors, of components forming a complete path of currents to travel, meaning that it is allowing energy to flow through a system. So when you plug in your phone with your charger, you are creating a circuit to the battery to allow that battery to charge up again. And we use the terms volts, currents, and resistors to kind of help. So there's a current running through your house, and there's a certain amount of voltage in which your phone can accept a charge. And once it's done, it's like, I can't take anymore. And so then it just says battery full. So, whoops, there we go. So as we talk about it, our energy, there's certain types of materials that are good conductors of electricity. That means allows the energy to flow through a system. And there are some that are just not as good, but great insulators, because sometimes these conductors can get extremely hot. So conductors allow electrons to flow freely from one atom to another. So it's kind of like a high five. These electrons, they just keep passing on their energy from one to the next to the next. So it allows them to flow through freely. And so you might remember, and I can pop back to it, our periodic table of elements. Mostly the elements in this section are great conductors of electricity. They normally are metals and metalloids, and they allow those electrons to flow through. So, and that's what this says right here. Metals are good conductors of electricity, where there are other elements that are not very good at allowing electrons to flow freely. And so sometimes we use them as insulators, which are just substances where electrons are held so tight to the atom that they cannot move from one neighboring atom to the next, meaning that there's just not, they are great potential energy, but they are not going to let that electron move through a system as freely as some of these metals would. So they're able to hold a charge for a long time. And so let me give you a picture of some of them. So, so think conductors and insulators. So allow energy to pass through them. That means metals. So our aluminum, our copper, our iron, our steel. So if you think about like an electrical current, we would do this in class where I'd give you a wire, a battery, a wire, and then just something simple, our conductor, our paper clip here. It's made out of metal. And then we could connect it all together to show that energy is moving through a system, create a light bulb. So that is electrical. And so if you remember, previously we talked about thermal energy too. And normally conductors are good thermal energy distributors. They, once again, will allow energy to move through the system. Whereas our insulators, they stop, or they don't let that energy move through the system very well. So insulators are glass, rubber, cotton, wool, plastic, paper. So if we were to try to do one of these, it would not allow that energy to move through a system. So that we replaced our paper clip with our rubber band. They are also great insulators, meaning that they want to hold the heat in. They do not want it to pass out through another system. It's going to hold it there. So that's why I use it. They hold that energy. So as we move through this, we're going to start talking just a little bit about the electrostatic series. So this is, once again, has to do with electricity and the static and how currents of energy can move through our protons, neutrons, and electrons. Once again, we're mostly looking at our protons and our electrons, and especially our electrons. And that's what this is saying right here. Electrons can be transferred from one object to another, and this is called the law of conservation of energy, meaning that it's exchanging and exchanging and exchanging. So they have the ability to flow freely a little bit more than the protons and the neutrons do, because they're housed in the nucleus. So law of electric charge, like charges are going to repel, meaning that if you have a negative charge and a negative charge, they're normally going to not work. They're gonna repel each other. And unlike charges are normally going to attract. So if you have a positive and a negative, they're normally going to come together. I think the easiest example of this is just a battery. So if you think about a battery having a positive and a negative charge, if you try to put the two positive charges together, they do not work for whatever you're trying to use the batteries for. But if you put them opposite, positive, negative, then you create an electrostatic series or a flow of electrons in a circuit that allow that energy to move through a system. So just to kind of give you an idea of some different things, these are two types of electrical charges, positive and negative. So this is a neutral charge. So if we count 1, 2, 3, 4, 1, 2, 3, 4, neutral. There are the same amount of positive and there are the same amount of negative charges. So they're neutral. They're happy to be together. When we get a negative charge, that just means that there are more negative energy sources than positive. And then if it's a positive object, clearly it's more positive than negative. So we can look at how static electricity can change by friction as we conduct energy through them. And so these are simple little demonstrations that you can kind of do to see the static electricity or the friction flowing through a system. So when two objects are rubbed together, so if you were to have like a comb or even just like anything plastic, a spoon, and you take a cloth and rub them together, you are generating energy. You're causing friction to occur. And as you cause that friction to occur, some of the electrons are going to gain and lose their negative charge and become more positively charged or more negatively charged. And as it does that, the charge then goes to the comb and it becomes static electric, and it allows it to pick up like simple little materials. This is an example of probably like paper or maybe some styrofoam in which it's been charged. You can do this too. So if you think about just walking across carpet with some socks on, rubbing your feet on the carpet as you walk, you are going to gain physical frictional charges. And then if you go touch someone, normally you can get a little bit of a shock or a little bit of a charge that kind of goes through the system. And this here is a Van de Graaff, and I'll show an example of that here later on in class. So this is a system where there's a rubber band that is moving through a generator right here. So it's kind of circling around up and down, up and down, up and down, like a simple little like conveyor belt, if you want to think about it that way. And this here is the top of the Van de Graaff, where all of the negative and positive charges are going to kind of be stored. And so if you were to touch something, this actually creates a really large electrical shock or static electricity, where normally you can kind of see that bolt come out. Same thing with water. If you run, just runs a faucet of water, and then once again, if you charge a like something that is made out of iron or metal, you can actually get the water to kind of wave back and forth, back and forth. So this one says here, attraction of neutral objects to charged objects. The positive charged rod, see all the positive charges, cause the electrons in the neutral water to shift, and so it's going to be pulled to it. This causes the neutral water to attract towards the positive rod. And then finally, electrical forces. This is our push or a pull. So we've talked about force before. Force equals mass times acceleration. We're going to look at it just slightly differently. So this can be created with a push, a force, or a repulsion, or a pull, a force of attraction. So negative or positive. The strength of the electric force is affected by the amount of charge and the distance. Force equals mass times acceleration. So kind of that same idea. As the amount of charge increases, electric forces increase. Direct relation. So the amount of charges increase, the electric force increases. The more energy moving through the system, the more energy there's going to be ready to be distributed. And as the distance increases, the electrical forces decrease, meaning that if you have objects that are further apart, so we've got our picture here, their distance has changed, meaning that there's not going to be as much of a force acting on them because it's been spread out further and further. And so we're going to demonstrate what some of this looks like as we move through the next couple of days, showing how electrical currents can cause different types of scenarios. So hopefully this was helpful.